Let's take a look at the structure of benzene. Firstly, benzene does not react with acidic KMnO4, so which means it actually doesn't have a C to C double bond. It also does not react with aqueous bromine, indicating the absence of C to C double bond again. And the enthalpy change of hydrogenation of benzene is negative 208 kilojoules per mole. If you look at it from the energy level diagram that was provided, it means that hydrogen, when it reacts with benzene, will actually goes down and produce your cyclohexane, and that's the amount of heat energy that's given. The other value to consider and look at is that if you were to take cyclohexene to react with H2, you'll find it's only negative 120. So cyclohexane has a 1 C to C double bond, while benzene has 3. So theoretically, if benzene structure is as indicated down here, then one would have expected the energy level to be such that when it actually reacts with hydrogen, it will release 360 kilojoules of heat energy. But it did not. The reason for that is because benzene structure is resonance stabilized, and as you can see down in this diagram, that you find that the pi electron is in actual fact hopping. So as they switch from this position 1 to position 2, it means that for each of the bond, it is neither single nor double. It is sometimes single, sometimes it is double. So we describe that by saying that it has a partial double covalent bond, which helps us to explain why it does not react with acidic KMnO4, because there's an absence of C to C double bond, as all the bonds in benzene between the carbon are all C to C partial double covalent bond. That also helps us to explain why it does not react with aqueous bromine. The last part is that in terms of the bond length between the carbon, it's also interesting to note that the actual bond length, when measured, is in between 0.134 nanometer to 0.154 nanometer, which means it's between the single and the double covalent bond, which again indicates why benzene actually has partial double covalent bond. Finally, the words that's used typically to describe benzene in the exam is resonance stabilized. The carbon atoms are all planar, and do take note that benzene is non-polar, as all the dipole moments cancel each other. Finally, benzene has numerous delocalized 6 pi electron, to be specific, 6 of them. And all these pi electrons, in fact, disperse themselves in the benzene ring, resulting in the fact that you get actually a partial double covalent bond between the carbon atoms. So benzene is electron rich, which means the benzene ring will attract electrophile. So benzene is stable, therefore it will undertake chemical reactions such that the aromatic system or the resonance stabilized structure remains intact after the chemical reactions. One of the chemical reactions that benzene undertakes is electrophilic substitution. In the electrophilic substitution, the first step is where the benzene actually is attacked by the electrophile. The way we depict that in the arrow, you have to take note, this arrow that's indicated down here, you have to take note is the movement of electron. So a full arrow indicates the movement of a pair of electrons, and this is where this pair of electrons will come up to bond with E+. Let's take a look at the movement of the electron. If you look at this diagram down here, okay, you can see that the 2 electrons that's down here actually move over so that the single bond can be formed between this C and actually the E+. That will allow us to create a carbocation, and this is actually called the uranium ion. So uranium ion is a carbocation. Okay, it is also an intermediate, which means it's stable, and quite clearly it's also resonance stabilized, as you can see that it has various resonance structures that's indicated down here. So uranium ion is positively charged. And in the next step, what we will see is that the uranium ion will loses its H+. So the act of losing the H+ indicates that uranium ion behaves as an acid because it is a proton donor. So in the second step, you'll get the deprotonation of the uranium ion, and the aromatic system will be restored, or the benzene ring will be restored. So in this case, you will now need a base. So the base will now actually accepts the H+ from here, but more important, you'll see that the electrons being returned actually. So how that mirror the movement of electron? Now we can use a purple line, all right, to indicate that the electron pair here is now being returned to the benzene. And consequently, what you get is actually the hydrogen that's bonded to the benzene ring is now being replaced with an electrophile.